bunch of little kids, grandnephews and nieces and things like this, and at least two of them had really snotty noses. So my wife and I were both trying to, play with the kids but not get too close. And she is sick today, but she had to go to work anyway because she had meetings. I've got a little sore throat and every now and then a cough, occasionally a sneeze, but I'm hoping I'm not going to catch what they had. Okay. Let me hit a couple of things before we get going today, and maybe you turn on the projector. I don't know. I guess I'll feel magnanimous since it was just Thanksgiving and that kind of stuff. And let's do a quick review. And let's see. 3 of the 7 of you, wait, I'm looking at the wrong one. No, far better. 5 of the 7 of you have turned in papers. All the ones that are present have turned in research papers. The 2 not here have not. 2 of the ones not here have not, so that's good. Test 1, though, not nearly as good. Only 3 out of 7 have turned in these, and I need those in as soon as you can get them to me. And test 2, the same 3 have turned those in, so y'all are 2 tests behind. And Leslie, do you have test 3 yet?
Yeah, I have test 3.
Okay, that's the one we're on now. So hopefully I'll have this to you by Wednesday, I believe. So let's move on this. Let's see if there's anything else. I can't think of anything else to do. Okay. This is, back on the paper issue, this is still November, so if you get the research paper into me, I'm talking to the people not here, obviously, because all 3 of you have turned them in, right? Nope. No. Yeah, you 3 have. If you get them to me this week, you still get that 1 extra bonus point that's left over, but next week, no bonus point, just get your score. Next week is the last week of the term, so that's the last week to turn it in without losing points. Okay. And also being the last week of the term, this week and next week would be great times to get those other 2 tests in. Like I said, I'll probably try to get you the 3rd test by Wednesday, and if I do that, then then next week will be a good time to get that test in, because the following Wednesday I'll be giving you your final exam, which will probably be your last chapter test. Whatever we cover in the next chapter, that'll be all that's covered on that test. So it'll be a pretty short test, I think. Yes?
Did you say that we are able to drop our lowest test score this semester?
Yes.
We
right.
are doing that?
Yeah. The paper doesn't count for it, and the final doesn't count for it. So that last test doesn't count. The 3 middle ones, yeah, the lowest of those. But don't say, okay, I'm just going to drop this one. Turn them all in, because let me be the one who drops it. You don't decide, because you might wind up doing better on one than you did on a previous one by surprise, and there you just gave up the opportunity to get a few more points. Okay. All right, any other questions before we get going today? We're on page 496. That's chapter 7, section 7.6, moment, center of mass, and centroids. These are applications of integration. Okay? Now, using a couple terms, kind of the math terms with the dynamics terms here. The torque, which we'll use more in physics and perhaps pre-engineering, or the moment, which you use perhaps more in math and pre-engineering, about the origin would then be, and this is given the symbol capital T. Now that's sort of interesting, because a lot of other texts use the symbol tau, which is the Greek letter T. It looks a lot like a T, but it usually has a curly Q to it. Let me see if I can remember how to draw it properly. Okay. Let me get my pen color changed. Okay. Tau, something like that. May have a few more twists in it. And that could be a tau naught just as well. So tau is equal to, okay. say, what is A here? I know what the mass is. This is, they're really being very physics oriented with it. Because I look at this and say, why have an A in there? Because A cancels out on both sides of the equation, so why put it in? But they're saying it's mass times acceleration, that is force times your distance from the origin. Now this is one-dimensional system. So distance from the origin. This isn't saying, like over here, the distance from the origin from a point up here. That doesn't follow that. It would be a distance from the origin on the x-axis, one-dimensional system. So that would be your mass one times your acceleration, whatever acceleration that one has, or this is the whole system acceleration, which it could be. I think that's what it would have to be, which, because they all go out, it doesn't matter anyway, times your displacement from the origin. So this is a torque about the origin. So that's what the O stands for, or the 0 stands for. That's what you're measuring the torque from. Plus M2A times so it's a force times the displacement, force times the displacement, force times the displacement, all the way down, and that's your total mass. And why they put the O there, I'm not sure. Times your, the total moment about the origin times A. Well, the moment is M1 x1 plus M2 x2 plus Mn xn plus all those. That's your moment about the origin times your acceleration. Well, on both sides. Well, so torque is your moment, which we were doing before, times your acceleration is what they're saying. So then you didn't want to divide it out. That gives you the torque about the origin. Or the twisting force about the origin. You can think of torque that way, torque twisting, that way, which is force at a distance. It's your lever arm, type thing. Okay. The center of gravity, then, would be your torque about the origin divided by the total force, which would be the sum of all these forces, which is, and that would just give you M0A from there, that's the torque, MA, which is the total mass times the acceleration here, that's of the system mass, and that would be, the A's cancel out, and it's the M0 over the total mass, which was exactly your x bar, your center of mass. So you can get it either by doing this, the moment about the origin divided by the mass, total mass, that gives you x bar, or you can do the torque about the origin divided by the force. So this is, without forces in it, it's this, with the forces in it, it's that. So the center of gravity and the center of mass have the same location. Wow. I was not even noticing they had changed from center of mass to center of gravity, because I use those terms interchangeably because they're the same. So that's why it snuck up and surprised me. They are the same values, center of mass or center of gravity. Gravity if you're talking about forces, mass if you're just talking about moments. Okay.
So what exactly is a moment again?
It's the sum of these things. Okay. M1 x1 plus M2 x2 plus M3 x3, all those, which is, you go back a few slides, this. M1 x1 plus M2 x2 plus M3 x3. That is just dealing with masses and displacements of those masses. Okay? That's your center of mass. The other term for that is a moment. Moment about the origin. I'm sorry, not quite the same. Moment about the origin is the sum of those products, and the center of mass then is that moment divided by the mass, total mass.
So like if I was going to push this desk,
right?
Then for the time that I was pushing the desk would be a moment.
Not a time. It's not that kind of moment. Trying to think of the terms they use in engineering when they do statics and dynamics. it's the product of mass times. Okay, if you remember back the kids on the seesaw, okay, your moment was the product of your mass times your distance from the fulcrum plus the mass of the other kid and his distance from the fulcrum. That's the moment, and that determines whether he's going to be up in there, you're going to be up in there, or you're going to be able to basically seesaw reasonably well. It's kind of like the twisting action of the product of your mass times displacements. I don't know if they ever gave a definition for moment. I don't recall that they did. What's that?
I believe it's for the game that I've seen. So going back to it, it was like the moment about point and moment about line. To define these two moments, consider an idealized situation which can is concentrated at a point. And this is between this point, mass, and another point.
Yeah. And there's the word I was looking for from the engineer. The moment arm. So it's the mass times the effective distance that mass is about from the point of interest. And you do this in statics and dynamics, but mostly in dynamics. You're finding the moment of the system. What is the point? And that's the center of mass is the point. But about a given point that's not the center of mass, the moment, how much does it tend to twist or favor that thing? And the distance there is the moment arm. That's the one they use in engineering a lot. And if you're trying to minimize the moment about a point, you try to get your moments on either side equal. You know, that gets to the statics case. The dynamics case is when they're not equal and you've got the twisting motion. All right. Thanks. Okay, that's where that was. I couldn't remember moment arm, which again has the word moment in it. But so here is on the top of 497, center of mass in a one-dimensional system. The moment in the center of mass, this is supposed to be two-dimensional systems. Why did it? Oh, I scrolled backward. I guess I scrolled back to get the other stuff. I didn't remember doing that, especially that far back. Okay. That's what we just had. Okay. How I got so far. Okay. Here's center of mass in a two-dimensional system. That's on page 497. Just happened to be on exactly equivalent slide, but for the one-dimensional. You can extend the concept of moment to two dimensions by considering the system of masses located in the XY plane at various points. X1, Y1, X2, Y2, X3, Y3, all the way up to X2 and Y2 in the master set. Now, rather than defining a single moment with respect to the origin, two moments are defined. One with respect to the x-axis, that's the moment above or below the x-axis, and one with respect to the y-axis, that's right or left of the y-axis. So in a two-dimensional system, there is a moment about the y-axis, that's m sub y. Here's the deal, and this is why I really don't like thinking in terms of moments too much, because the moment about the y-axis is how far you are on x, okay? Because about the y-axis, then that's the distance in your x, and the moment about the x-axis deals with how far you are in y from the x-axis. So the names are not the variables that you use. The two-dimensional system is the moment about the y-axis, m sub y, which you're going to get by summing up your masses times the x values, and the moment about the x-axis, that's your m sub x, and that's going to be formed by the mass times your distance from the x-axis in your y's. So it's something you just have to keep in mind. If you talk about moment with respect to the x-axis, then you're going to use your m1s, y1s. Moment about the y-axis, you're going to use your, I may have said that backwards, repeated it. Moment about the y-axis is going to be your m1, x1, m2, x2, all like that. Moment about the x-axis is going to be your m1, y1, m2, y2, and so on like that. So it's the opposite letter or variable that you're dealing with. So, how to extend what we were just doing, that you have your endpoint masses, M sub 1, M sub 2, up to M sub n, located at n different positions, x1, y1, x2, y2, x3, y3, up to x sub n, y sub n. Okay? The moment about the y-axis, M sub y, is the sum of those moments. Okay? M1, x1, remember, with respect to the y, it's the x's you're dealing with. M sub 1 times x sub 1 plus M sub 2 times x sub 2, so M3 times x3 times all the way up to Mn xn. Adding those moments together. That gives you the moment with respect to the y-axis. The moment about the x-axis would be your M sub x, which is, and remember before it was M sub 0, that was about the origin when it was just one dimension. Now we're doing M sub x and y about align the axes, and this would be M1, Y1 plus M2, Y2 plus M2. So I tend not to talk as much about moments here because the notation just seems to me backwards. So I think about more in terms of center of mass or center of gravity again. So the center of mass or center of gravity, x bar, y bar, this is going to be some point out here in space. Now you can have masses anywhere. Well, mass here, mass here, mass there. And your center of gravity might be a mass over here or down here or something here. Not any of those and not on either axis. Okay? It'll have an xy component as well. And the x bar is going to be the M sub y, the moment with respect to y divided by the total mass, the y bar, the M sub x divided by the total mass. And that's why, because the letters are kind of backwards, I just think of this as M1, X1. Here, I think of this as the numerator here as being that sum, and there your x's are all involved, and this one is the sum with all the y's involved, and then divided by the total mass. And that's, I just jump and write in that form rather than thinking in terms of moments. But I'm not an engineer, okay? Whereas the total mass is the sum of all your masses, total mass of the system. Okay. So again, what is a moment with respect to x or y? It's the weighting that you have, where is that point, that center of mass located? Where is it weighted toward? Okay. The moment of a system of masses in the plane can be taken about any horizontal or vertical line. It doesn't have to be about the x or y axis. In general, the moment about a line is the sum of the product of the masses and the directed distances from that point to the line. So, if you're doing the moment about the line y is equal to b, y is equal to b could be up here or down here or somewhere like that, then it's the product of whatever mass you have times the difference between this y1 and, the y1 up here, that would be this one, and the b. Now, if b was down here, then that would be minus or minus would be plus, that would be a longer distance. The b's above, on the same side as this, that would just be. So this takes care of it all. M1, y1 minus b. Moment about the line y is equal to b. And then it would be M2 times y2 minus b, y3 minus b, Mn times Mn minus ym minus b. Sum of all those. The moment about the line x equal a, whether a is over here, wherever that is, then it would be the mass of that point times the distance that is from the line x equal a. Okay? And the x minus a there, 3, all the way out. Now that's getting to be a bit more convoluted, but it still works pretty well. Especially if you note that there's an M1 minus L, so it's M1 X1, M1 Y1 plus M2 Y2 plus M2 minus M1 B1 plus M2 B. So it's basically the mass about the axis minus the mass about that point, okay, that value there. It's another way to look at it, if that's helpful or not. Okay, so here's example 3. Find the center of mass of a system of point masses where M1 is equal to 6, M2 is equal to 3, M3 is equal to 2, and M4 is equal to 9. They sort of made their circles proportional to the masses, you might say. Located at -3, -2 for x1, y1, 0, 0 for x2, y2, -5, 3 for x3, y3, and 4, 2 for x4, y4. Okay? Find the center of mass. So it's not about any point, the center of mass. So how would you do that? Let's do the x bar first. What would be your equation for what x bar would be? All right, if you want to do moments, we can do moments, but to me it's just as easy to say it again. M1 x1 plus M2 x2. Is that what you're saying? Yes. Plus M3 x3 plus M4 x4. Perfect. Over.
Would be your total mass.
Total mass. I'm just going to put little m. Okay. Now M1 up here was 6 times 3 plus, and the next one's real easy, 3 times 0 plus 2 times a -5. You go. What's next? What's the last term? Anybody?
You have 9. And
4. Perfect. All over, and your total mass is 9 and 9 is 18, and 2 is 20. Made a nice round number there. So this would be 18 plus 0 minus 10 plus 36 over 20. 18 and 36 would be 54 minus 10 is 44 over 20, which would be 2.2. Is that right? Go to my head. My head hurts. Okay. I believe that's 2.2. Yeah or nay? Okay. All right. Now, 2.2 would be somewhere right along in here. Does that look reasonable? Boy, seems like it's really heavily weighted toward these two. Well, you got 2 out here. This one's not contributing much to that. You know, this one over here, but that's such a small mass. These are pretty good sized masses. So yeah, that at least makes a little bit of sense there. Okay. How about the Y bar? What is your Y bar? How would it go?
maybe 6 times -2.
Got it.
times 0
right?
plus 2 times 3
All right.
plus 9 times
2. Okay. And that would be, and you don't have to do them again, that's still 20, okay? Mass hasn't changed any. That's minus 12 plus 0 plus 6 plus 18. That adds to 24 minus 12 is 12 over 20. Which would be 3 over 5, which is 0.6. So that puts it just above halfway here. So the center of mass would be somewhere about right there. Okay. And again, that seems heavily weighted in this direction, but that's where most of your mass is. This is a smaller mass here than either one of those by half and by a third of those. This is even smaller. This is a third and less than a quarter of what that is. So even though that seems to be heavily weighted this way, that kind of makes sense. You got more mass above the line than you have below the line, more mass to the right than you have to the left. So that sort of makes sense. Okay? Let's see what they got. They left it as fractions, okay? I never would have thought they would, but that was here. What do we say that was? 44 over 20, which is 11 over 5, right? And this was, that's X bar, Y bar was 3 over 5. I said it earlier and I couldn't remember what I said. 11/5 and 3/5. Perfect. Okay? And so the center of mass would be the point. How does this book call it? It doesn't. I've seen it called COM. Okay? That's not a .com, by the way. That's center of mass. Occasionally, I think I've seen a C sub M or something like that. But anyway, that would be a point, 11/5, 3/5. And that would be the point if you took this plate, or a massless plate that had those 4 masses on it, and put your fulcrum here, it would balance perfectly. I don't know if fulcrum's the right word, but that's what I use. Okay. All right, to erase this. All right. Let's see how they do it. M1. Oh, they're adding all the masses together to begin with. Perfectly fine. Good thing to do, 20. We did it later, but that's fine. The moment with respect to the y-axis is your m's times your x's. So it's 6 times 3 plus 3 times 0 plus 2 times -5. Sorry, plus 3 times 9 times 4. I can't even read. That comes out to 24, exactly like we did. M sub x, moment with respect to the x-axis, which is your masses times your y values, which is 6 times -2 plus 3 times 0 plus 2 times 3 plus 9 times 2. That came out 12, just like we did. So your x bar was 11/5 and y bar was 3/5. Center of mass is the point 11/5, 3/5. Oh man. Ugh. Okay. Now, those are for individual point masses, which there may be opportunities or places where you deal with things like this. Much more common, we have sheets or rods or things like this, which is a continuum. Well, therefore, you get away from products to integrals. Okay? Individual places to and integration of places. So this is what we're going to talk about here, of a planar lamina. Planar means it's going to be in a sheet. They're not dealing with rods. They're going to go straight to sheets, which is two-dimensional. And it's a thin, flat plate of material of constant density. That takes a lot of the difficulty in the calculations out. Not that that adds a lot, but it does a little bit. That's called the planar lamina. Density is the measure of mass per unit volume, such as grams per cubic centimeter. But for planar laminas, it's the density is considered to be a mass per unit area, because you're only dealing with a surface, okay? If you had used a rod, then the density would be mass per unit length. Okay, so you have all this. So the density is often denoted by the symbol rho, which doesn't look like a D, or it looks like a P, but it really corresponds to an R, and it has nothing to do with why they chose rho, but they always use it. Lowercase case Greek letter rho. Now, if it's a linear density, to me that should be rho sub L. If it's an area density, it should be a rho sub A. A volume density, just rho. That's the one you usually do rho. But if you want to be more specific, rho sub V. But they use this rho for this lamina, which is a density per unit area. Okay. So you can think of the center of mass, X bar, Y bar, of a lamina as its balancing point. And if you have a circular lamina and you have equal density all the way around, all over the whole sheet, then the center of the circle is going to be your center of mass. Almost without thinking, it would be. Okay, if you're doing a perfect square, then the intersection of the diagonals. Or even, I guess, a parallelogram or any other regular figure like that, that would be, your center would be exactly your center of mass, because your density is even throughout that. Okay? So a lot of those you don't even have to use a formula for. But if you had some weird old shape, like let's say you had the ceiling in here as a plane, but you wanted to cut out that block over there, and you wanted to talk just about that. That's not a regular shape. It looks like it's longer this way, shorter that way, but it still would be rectangular. Well, but let's include that thing there, okay? So now you have a really weird looking thing there that you can't say, here's its center, okay? Or not easily, okay? So, this is the real simple case. All right, consider it an irregularly shaped, that's what I was just doing, planar lamina of uniform density rho, and that's the area density, by the way, bounded by the graphs of y is equal to f of x on top, y is equal to g of x on the bottom, and where x is going from A to B here, these both happen to be positive values, don't have to be, but it could be, is shown here. The mass of that region would be the density at rho that you had there times the total area. Well, we already know how to do area, remember. That would be the integral from A to B of the difference between the x's and y's times your dx. The difference between here and here is the length. The dx would be your width, and the sum of all those would be the integral from A to B of that thing. That would be the area. So rho times the area would be your total mass of that region. Where A is the total area of the region. That's the easy part, okay? The mass. Now we have to deal with to find the center of mass of that lamina. We have to partition the interval from A to B into n subintervals of equal width, delta x, just really like we did before. Let x and I be the center of the ith subinterval. You can approximate that portion of the lamina lying to in the I subinterval by the rectangle whose height is alpha of x minus alpha of x of I minus g of x of I. Okay? Which is exactly the difference that we had when we were doing the area. And because the density of the rectangle is rho, its mass is rho times the difference of these two times delta x. Hey, it's exactly what we were doing before. Okay? So why are they going through this again? Now, considering that this mass to be located at the center of x of I, y sub I of the rectangle, the directed distance from the x-axis to x of I, y sub I would be y sub I, and that would be the average of these two. That's the sum of f and g divided by 2. Let's go back and do here. Okay? This is showing what we just said. To get the total area, you just do the integral from A to B of all these strips all the way across and multiply by the density. That's the area density selected the total mass. Now to get the center of mass, we do the whole area of this thing just like we did before, but then we multiply it by this midpoint, okay? Because that's where the center of mass would be located, okay? Because that's a uniform density, right? It's an even plate, so the center of mass of this strip would be the center, which would be f of xi plus g of xi divided by 2. That puts you in the middle. So you have f of xi minus g of xi, that's the length, and then when you multiply by the location, you might say, of that y sub I, that would be the sum of those two. Same two numbers, but the sum, half of the sum rather than the difference. Okay, so that's why your equation now, so this is your moment now. Remember, the moment was mass times distance. The mass was this part, rho times the thing, just like we had before with the dx in there, okay, delta x. Times your y sub I, and your y sub I is that sum of your endpoints divided by 2, the average value. Okay. So that then gives you your moment. Okay. Now, so let's start over here. Let f and g be continuous functions such that f of x is always greater than g of x, greater than or equal to. They can't overlap. They can touch, but they can't pass each other. F of x always greater than or equal to g of x on A to B. And consider the planar lamina, uniform density rho, bounded by the graphs y is equal to f of x on top, y is equal to g of x on the bottom, because f of x always greater or equal to g of x, and x is between A and B. Same figure we had before. The moments about the x and the y axes are then, about the x axis, rho times the integral from A to B of your average displacement on y, which is the sum of those two divided by 2, times the incremental mass there, which is rho times the difference times that. Okay? Now, that was the m sub x, moment with respect to x. This is always dealing with y's. Remember, these are sum of y's, the average of the y's, the sum of the difference of the y's. Okay. Now, how about the moment with respect to y? Okay? This part, the rho difference times that, that are exactly the same. But now the moment with respect to the y-axis, it's just your x value. Okay? So going back to your illustration here, that's just for the strip that's here, that's its mass, that's its displacement. That's its mass, that's its displacement. It's just the x value along here. So that makes the m sub y, moment with respect to the y-axis, is just the x's then. Oops, did I go too far now? Yeah, I did. Sorry. Yeah. What is this one? There's your volume, or your volume. Height times width times density. The mass, okay? And then it's x, the displacement, mass times displacement plus your moment. So, what's the center of mass then? Is for the x bar is the m sub y, which has all x's in it, divided by your total mass that we did on the previous slide. And the y bar is the m sub x's, which has these are distances with respect to y. The road, this stuff, the total mass is the same. This is your x, that's your average y. And the total mass is just your road times that length times width. The mass of the lamina. All right. I don't know if that's helpful or not. I think doing them a few times may make it come to life a little bit better. Find the center of mass of the lamina of uniform density road bounded by the graph of f of x is equal to 4 minus x squared and y and the x-axis. Okay? So, I think we probably need a picture, don't you think? Or thousands of words, right? Okay. F of x equal 4 minus x squared. What would that look like? I have drawn my picture poorly. Okay, let me erase this and the x-axis. So let me put it here. Okay, say that again now.
It would be up 4 on the y.
Okay, when x equals 0, 1, 2, 3, 4. There you are on the y-axis. Okay? X equal 1.
Be 3.
1, 3. And negative 1, 3, right? X equal 2.
2.
Second.
2.
Second.
X equals 2.
Yeah.
Oh, no, 0.
0, okay. And 0 here. So I didn't need those extra ones out there. So this is, what would you call that shape? Parabola. Okay. Find the center of mass of the lamina of uniform density road bounded by the graph of that and the x-axis. So that's the lamina we're talking about. Now mine doesn't quite look symmetric, but that's because of my lousy drawing. Okay? Get over it. Okay. Now, here's something you can do, okay? Because it's a uniform density, the whole plate, and that is symmetric about the y-axis, can anyone guess what x bar is?
0.
0! You got it. That's right.
Yes.
Okay. Okay. So without further ado, your x bar is 0. You can look at it by symmetry. It has to be. All right. So, what we have to do is your y bar. Okay? Now, it's a ratio. Has a numerator and a denominator. Which you want to do first? Do you have a preference? Okay. I do. I like to do the denominator first. The mass is the easier thing to do. Remember, rho is a constant, so it can go outside. And what's your limits here?
From 0 to 2.
I think it's minus 2 to 2, isn't it?
Well, couldn't we do that? I mean, it's better to have 0 in there.
Okay. And then double that. Okay. You could end the mass. That's fine. The moments, I don't think you ought to there. Okay. But you could do it there. So if you do a 2 down here and do a 0 to 2 here, and those are going dx's. Those are limits on the x. So that's going to be perfectly okay for your mass, because whatever the mass is on one side, it's going to be the same on the other side. Moments, I wouldn't try it, okay? Because you have to include the whole deal, I think. Okay. We'll go back and check, maybe. Okay. What goes there? So we're just doing half of this. Just imagine your little rectangle here. What is the length of that rectangle?
It would be the delta x.
Okay, the thickness would be delta x. So I've got the dx there. It's just the functional value there, isn't it? Minus 0. Here to there. That's the length. And the top is 4 minus x squared. Right? Okay? And here's Daniel. Everybody's getting back from Turkey Day. Good. Mrs. Charles and Mrs. Jordan. All right. We're doing example 4, which is pretty much the top part of page 499 in section 7.6, moments, center of mass, and centroids. Chapter 7 is applications of integration. Okay, so there's your length times your width. That's it, folks. There's your integration. Like I said, this is the easy part. Length times width, that's your area, times your density, area density, and that gives you your total mass. So this would be 2 times rho times, what's the antiderivative of 4 minus x squared?
-2x.
4x minus,
Oh, it would be x to the third over 3.
over 3. Is that what you said? Yeah. Okay. And we're going to evaluate that from 0 to 2. All right. It'd be 2 rho times 4 times 2 is 8 minus 8 over 3. And then I'll do the 0 part, minus 0 plus 0. Okay, done. Now what would that give us? 2 times rho, and that would be 2/3 of 8, right? 1 of 8, 1 times 8 minus 1/3 times 8 is 2/3 times 8, which would be 4 rho, no, 32 rho, 4 times 8 over 3. 32 thirds times rho. All right. Yeah, 32 thirds rho. That's your mass. Okay? Now we've got to do the moment with respect to the y-axis, which is your distances from x from each one of those. Okay, you know, now I may be wrong on this, but I think, I don't know. Let's see. That numerator is just going to be your row. This time let's go -2 to 2. It may be okay to use the other way. The only difference is here you have x, because that's your distance here, times this mass, that's your moment. And the distance from the y-axis, that's your m sub y, nope. It's distances from the x-axis. That's what you're doing for your y-bar. Sorry about that. That's going to be your midpoint. Wherever you happen to be, that's your midpoint. So it's not x. It's I think it may be okay to double it again, because let's just do it this way for now. The only difference is this part's the same. We're changing the integration so we don't have the 2 out there, but the 4 minus x squared, that is exactly the same dx. That part's the same. The part that changes is what's your displacement from the x-axis, and that is the center there, which is the sum of those two divided by 2. Well, 0 is 0, so it's this thing, 4 minus x squared over 2. Yeah. No. Yeah, 4 minus x. The part that's missing is the plus and minus, but it's 0 in both cases. So now the numerator is going to be rho over 2, okay, because that 1/2 can come out, and it's the integral from -2 to 2 of the product of those two. Sorry, I already took the 1/2 out, so it's just going to be 16 minus 8x squared. Is that right? Plus x to the 4th. And because those are all, yeah. You got me convinced again, whether you meant to or not, to go on and do it 0 to 2. Because that's even function. So you would have had a 2 out front. That cancels the 2 that you bring out. So it's just that integral. And what's that integral? Rho times antiderivative of 16. 16x minus sorry, my throat hurts so badly. Anybody? Second. Antiderivative of minus 8x squared.
And -16.
Okay. Not taking derivative, the antiderivative.
It's going to be 8x to the 3rd over 3.
Over 3. Perfect. Plus
X to the 5th over 5.
x to the 5th over 5. Okay. Evaluate that from 0 to 2. I changed and went back to 0 to 2, took the 2 out front, canceled the other. Okay, so this will be a row, and when you plug in a 2 there, you get 32 minus 8 times 8 is 64 thirds. Y'all, I'm doing this in my head, so don't let me screw up. I believe that's right. Plus, I think it's 32, isn't it? Okay. Now, we can either do least common denominators or let y'all, I see you already poking on your calculators. I think I'll let y'all do that one. Weird number, right? What does it come out to? Oh, still working on it. Okay. Okay, obviously the least common denominator is 15, right?
We got 256 over 15.
Okay, 256 row over 15. Got it. That's what the book got to. So the y bar is that moment divided by the mass, which is 32 row over 3. Okay? Now the good news, the excellent news, the rows go out. So it doesn't matter what that density is. You can count it as 1 because they always eliminate as long as it's uniform density. Okay? You can divide your numerators, and that will be a 5 down here. And you can divide, I think you can divide 32. Let me think back on this a bit. 256 is 2 to the 8th divided by 2 to the 5th. I think that's 2 to the 3rd. 8 times. Nope, that's not right. Oh, had someone divide 256 divided by 8. What do you get? I'm sorry. 256 divided by 32. What do you get? 256 divided by 32.
8.
8? Okay, I did it right. Yeah. I don't know what I was thinking. Okay, so this will be 8 fifths. 8 fifths. All right. Yep, and that's what they got too. Now 8 fifths, that's 1 and 3 fifths. So about a 1.6. Something right about there. Actually, where I drew my line is not far from off. And it's on the x-axis, on the y-axis, because x bar was 0. So there's your y bar. So your center of mass is 0, 8 fifths. Say 8 fifths and right 5/8. Okay. I don't know where my brain is today. That's your center of mass. somewhere right around there. Okay? Now, the hardest part of that was the fractions on the calculations, the arithmetic part. The calculus part really wasn't that bad. A little bit at the beginning of the conceptual thing, but once you got that down, the calculus part was easy. Okay?
And so, why was our g of x 0?
Well, because we said and the x-axis. So the x-axis is y is equal to 0. See, there's y is equal to this, up to x equal to that, and g of x is equal to 0. Because the x-axis is where y is equal to 0.
But if it's two, like in this picture right here.
Okay, yeah, then the g of x is definitely not 0, right? Yeah, that would have been a lot more complicated problem because even in the mass, this is the f, you'd have to subtract the g from that before you multiply by the x, so that would have more. Up here, you would have that subtracted the g plus the average between f and g, so that would, it would be quite a bit more to do, which may be leading us to the next example, okay? Oh, no, okay, I'm sorry. The balancing point, if you took that thing and laid it down, and put it on a pencil point, right there at that place, not mine, but theirs, it would balance perfectly right there, if it's an absolute uniform lamina. Now, another name, sorry, for the center of mass of a laminar, planar lamina, which means uniform density, that's called a centroid. And forgive me if I ever mispronounce that. I take a thyroid medicine called Synthroid, and I always want to call this Synthroid rather than Synthroid. And then I wound up calling my medicine Synthroid, not Synthroid. So there's an R in one and not in the other. So, well, no, there's an H in one and not in the other. There's an R in both of them. Yeah. And it's spelled different. It's S-Y-N. It's synthetic thyroid, Synthroid. Okay. So let's move to, oh, wait. Let's see how they did this problem. Forgot this was on here. So, because the center of mass lies on the axis of symmetry, you know the x bar is equal to 0. Always do that if you can. If you can't, don't do it, okay? But if there's a perfect symmetry, then take advantage of it. Moreover, the mass of the lamina is that, which is exactly what we did, except we did it half of that and doubled it, right? We did 0 to 2 and doubled it, which they did it their way, and it came out the same thing, 32 rho over 3, okay? Now, the moment about the x-axis that's going up, they drew their little rectangle on this side. It didn't matter where you drew it, but the moment is the mass times the displacement. So pick your rectangle anywhere you want to draw that rectangle, and then its mass would be just like the thing before, f of x minus 0, which is just f of x dx. Okay, that's the mass. But now its distance from the x-axis, because you're doing the moment with respect to x, then this will be 1/2 of that, which is f of x divided by 2, which is that thing divided by 2. That's how we got that. So your distance from the x-axis is the center of the rectangle, which is f of x divided by 2, which is what we did as well. And because the mass of the represented rectangle is just like we had before, rho times the height times the thickness, then your moment is that rho times the height times the thickness times the distance from the x-axis, which is that height divided by 2. Now, the reason I back off Clark had first said, let's go 0 to 2 and double it. The reason I wanted to hold off on that, I wanted to make sure that this was an even function as well. You can do that with an even function. You can't do it with an odd function. And as soon as I then got to thinking about it, this times this, there's still going to be an even function. Sure, let's pull it out. So if you pull out, go 0 to 2 and double this, but then pull out 1/2, they both disappear. And that may have been, y'all seem to stop when I did that, like, why is he doing that? How can he do that? But they are not doing half of it, so they're doing -2 to 2. And that's the same thing we got. They pulled the 1/2 out, and they did that. And that's the same integration we did, okay? And then they just suddenly say that's the answer. And it is exactly what we got. So the y bar is in that moment, that divided by the mass, which was this, and that gave us 8. The rows disappear, 8/5. So the center of mass, and I thought this was a different thing because it wasn't uniform, but they just laid it down like this. Put a pencil point, 1 3/5 up this way, on the y-axis. Put a pencil point there, and you can balance it perfectly. The balancing point or the center of mass. Okay, got it? Yes, sir.
Sorry to interrupt.
Yeah.
I was wondering, Dan, you've been continuing with me after class. Yes. What time y'all get out?
11:15, isn't it?
11:40.
11:40. Sorry, 11:40.
Okay, see me at 11:40.
Okay.
All right, Doc. I appreciate it.
Do you need the key?
In the lab downstairs.
Do you need the key or?
Just lock it.
I can't remember. It was too long ago, but just in case I won't need it.
We'll be ready just in case.
Okay, I won't need it back until I'll pick it up from the way down. If you're going to be down there.
All right.
Okay.
Appreciate it.
All right.
Sorry to interrupt.
All right, no problem. So the center of mass of a lamina, I thought we already had done this, of a lamina of uniform density depends only on the shape of the lamina, not on the density for that region, for x bar, y bar. It's called the center of mass, or the centroid, sometimes called the center of mass of a region in the plane, or the centroid of that region. In other words, to find the centroid of a region in the plane, you simply assume the region has a constant density. And why not rho equal 1? We just saw what happened. Rho winds up in the numerator, rho winds up in the denominator, they cancel out. Whatever that rho was. So just assume it's 1. Compute the corresponding center of mass. Okay? Henceforth, you don't even have to throw the rho in there. You can if you want to conceptually make sure you got all the pieces in place, but if you just understand that's going to cancel out, so you can count it as 1, not necessary. All right, it looks like to me they're skipping examples 5 and 6. Ooh, yes, huh?
Not us.
What's that?
I'm just saying, not us.
Not us, of course not. We wouldn't think of doing such. So let's see if we can get it here. Find the centroid of the region bounded by the graph of that very same graph we had. Why did I erase it? But then we have another feature in it that's not the same as what we had. So let's do our graph here. We went 1, 2, 3, 4. Okay. And we went 1 and 2. 1 and 2. And we got this part down. Something like that. The only difference is the g of x is now x plus 2. So when x is equal to 0, g of x is 2. When x is equal to 1, g of x is 3. I think that's the point right there, isn't it? Okay. And when it's -1, it would be 2. No. -1 would be 1. and 0, negative 2 would be 0. Okay, so there's your g of x. So now we're not interested in this at all. That's out of the picture. This is the portion we're interested in. No symmetry here. Okay, so we're going to need to do our, and which you want to do first?
Let's do one that we didn't do last time first.
The mass. Yeah, let's do the mass first. I agree with you. Okay. Okay. Here we're going to have a representative rectangle like this. Okay. All right. I'll put that dot in for later. It's not for now. Okay. But for right now, it's the mass. I'm going to call it capital M. That's, so they finally got around. No, they didn't. They still called it little m there. But somewhat, no, I guess not. I've always called that capital M, and that's why I keep wanting to call it that, but they're calling it little m, so I'll call it little m. Okay. Okay. And that's going from, this time, the x is going from negative 2 to what? 1, not 2. Okay? You don't have to pull a row out. The row is 1. Row is immaterial. Don't worry about it. Okay? Now it's going to be the length of that, which is 4 minus x squared minus x plus 2. That's your f minus g, right? Let me write this down. The f of x is the same as before, 4 minus x squared. And the g of x now is x plus 2. That was it, right? Yeah. And then your thickness is dx. That's the easy part. Okay? So if you do this, do the simple math first, minus 2 to 1, what will be your integrand now? 4 minus 2 is 2 minus x minus x squared. Right? Yay or nay? What's that? Yes, okay, times dx. All right, and that's not an impossible integration to do. In fact, it's pretty easy. And what would that be? I thought it'd be pretty easy. I was hoping it would be pretty easy. Where did you get your 8? Oh, are you going on and evaluating? No, let's not. Let's just integrate first. Antiderivative.
X.
2x minus x squared over 2 minus 3, right? We're going to evaluate that from negative 2 to 1. No shortcuts here. Okay. Do the 1 first. And what do you have? Pretty easy. I thought it was 2 minus 1/2 minus 1/3. Then you have a minus with a minus 2 in there. That would be
and plus.
Plus 4. Okay. Plus 2, right? And then a, I think that's a minus, isn't it? It's a minus, which is a plus, but then when minus 2 cubed is a minus 8, so that'd be minus 8 thirds. Is that right? I hope it is. All right. Ooh, yuck. Oh, no, not bad, not bad, not bad. Oh, a little bad, but not too bad. So that would be an 8 is your whole numbers, but let's do that minus 9 thirds, which would be a minus 3, and then you got a plus 3 halves, isn't it? All right, so that's a 5 plus 3 halves. That'd be 13 halves. Let's see if that's what they got for their... Nine halves. Got the same thing. I must have... Made a dumb sign error somewhere. Oh, no.
Yeah, put what we had in the calculator and came up to 9 halves.
Okay. It's 9 halves. I don't know where I made my dumb mistake, but I did it somewhere. That's why calculators are smarter than me. Okay. All right. Let me just think through this a minute. 2 minus 1 half minus 1 third. We got that part. And then did you do a plus 4 and a plus 2 and a minus 8 thirds?
1, 2, minus 3, plus 4, plus 2, minus 8 over 3. 9 halves.
Okay. 4, 6, 8, minus 3 is 5. Okay. I'll believe it, but I don't know where my numbers are messing up. There's messing up someplace, and it's probably something really obvious, and I just did. Anyway, there's your mass, whatever it is. Okay. Now, got to do the X bar and the Y bar. Okay, the X bar is the distance from the Y-axis. So this is called the moment with respect to Y. But I just as soon just write down what it is. Okay, that's the integral from minus 2 to 1 of exactly the same thing they have here, which is going to be this one. Okay, so the 2 minus x squared and the dx, they're going to be in there. Okay, and what's that multiplied with out front? Okay, there's your area of that thing. And now what you multiply this distance from the y-axis, that's just x. So it's x times that. Okay? Which will then be the integral from negative 2 to 1 of 2x minus x squared minus x cubed dx. So when we do the integration of that, or antiderivative of that, that would be what?
mixed up on how we got there.
Okay. Okay, when we're doing the X bar, okay, that's going to be this mass times its distance from the y-axis, which is going to be x. It's x this way or x that way. This way, okay. From here to here, any of those x's, that's the distance times that mass. So, it's just multiplying x by that same thing. See, here was our mass. This times that. Length times thickness. Well, you got your length times thickness there, but now you're multiplying, that's your mass times your distance. That's what your moment is, mass times displacement. Okay? The distance here is just simply x. So you're just multiplying x by that. So that gives you that integral now, 2x minus x squared minus x cubed dx. And what is that antiderivative of that?
X squared over 2.
Yeah, which is just x squared, right?
X cubed over 3.
Right.
X to the 4th over 4.
From minus 2 to 1. Okay. Here we go again. All right. 1 would just be 1 minus 1/3 minus 1/4. Minus, whoa, this is going to be a negative this time. That's going to be a minus 4. That'll be a minus, another minus, minus 8/3. And then a minus is going to be a plus. 16, I think, over 4, so that's just going to be a plus 4. So the plus 4 and minus 4, I think, cancel out, and that would be a 1 minus 3 minus 1/4. That would be a negative 2 minus 1/4, or negative 9/4. No, yeah. I seem to have blown it again.
What do you mean?
No. Oh, okay. No. I think they didn't do what I'm doing. Okay. I believe that is negative 9/4. Let's try it. Divide it by a positive 9/2. And you get a negative 1/2. And that's what they got. Yes. I got it right that time. Okay. That does come up to positive 1/2 now. Sorry, the scratch is all over the board because I don't have enough room. But
Why is it?
what's that?
Why is it divided by 9/2?
Because they went on and divided by the mass, and the mass was 9/2. Remember?
Yes, sir. I remember that.
Okay. So we got a negative 9/4 divided by 9/2. And that came up negative 1/2. So that's your x thing. And basically, luckily, I went right about negative 1/2. That's where I drew my rectangle there. I didn't intend to do that, but I almost got it on there. That's where your x bar is, negative 1/2. Now to do the y bar, that's the more difficult one to do. And I've got to erase some stuff to do it. Okay? So, not what I wanted to erase. Okay. I'll go back and draw that in again. And let me erase all of this. Save my mass of 9/2. Okay. I'll erase some of this down here too, because I won't need that anymore. Okay. I don't think I need this either. Yeah. Alright, let me go back and draw in what I need to draw in. Okay. Ooh, that looks quite a bit different, doesn't it? Alright. Now, your Y bar is the same match as the match that's in the curve. I've lost the curve here. Same mass, that's what that represents. But now we need, that's the same as that thing up there. Okay, that's why I left that here. Now we need to multiply this by its displacement along Y. Okay? And that's going to be the average value here, which is going to be your f of x plus your g of x divided by 2. That gives us that value there. Okay? Because it's the distance this mass, or the average of the mass, is above the y-axis. Oh, man. Oh. So in this case, this is your x, which is, I'm sorry, not x, f, which is 4 minus x squared, minus your g, which I'm afraid I erased, x plus 2, right? And then we're going to divide that by 2. Okay. I'm going to get that 2 out front. Okay. So that's going to be 1/2 the integral from minus 2 to 1. And let's do that math while we're doing it. That would be 4 minus 2 this time is 2. And no, it isn't. That's a plus. That's a plus in there. Sorry about that. We already did the minus. It's the sum divided by 2. That's how you take the average. Okay? So it'd be 4 plus 2 is 6. Plus x minus x squared times 2 minus x squared times dx. A much less favorable integrand here, because we got to multiply two trinomials together. So you want to do that down here, the 1/2, the integral from -2 to 1. So let's multiply. That's going to be a 12. Okay. Minus 6x plus 2x would be a minus 4x. Agree with me so far? What's that?
Minus 6x squared.
Okay, yeah. I'm going to get there. I was trying to do it all at once. So if that's confusing, I did my x terms, which is the constant term, which is 12.
Right.
And then the x term was minus 6x plus 2x. That's going to be a minus 4x. Now I'm going to do the x squared terms. Okay? And that's going to be my minus 6x squared minus another x squared minus a 2x squared. right?
9x.
No, 6x squared minus 3x squared, it would be plus 3x squared. Again, I may be inviting myself to have real serious problems here, but so it's a minus 6x squared. Oh, wait, that is a minus, I'm sorry. You were right, minus 9x squared. They're all minuses. So you're right, it's a minus 9x squared. Duh. Where is the brain today? Okay. Lost in space. Still back there eating turkey, I think. Okay. All right. Let's see. Minus 6x squared minus an x squared minus 2x squared. So that's minus 9x squared. So let's do our cubic terms. 6 is used up now, so it's through. But you got a minus x cubed plus x cubed. If I'm doing it right, those add to 0, right? Minus x cubed here, a plus x cubed there. Okay? So I think they add to 0. And then my x fourth term is going to be a minus x fourth. Now, do you get that or not?
Be a positive x to the fourth?
You got it, plus x fourth. Duh. Okay. Now, did I account for every term? I got 6 times 3 of the terms. I got x by 1, 2, but the third term went to 0. I got this x squared covered. That x cubed went to 0, and then a plus x fourth. So that's right. Okay? Now let's integrate that baby. Okay, and then my dx is out here by itself. Okay. All right, how does that integrate? You have the 1/2 out front.
x
12x
minus 4x squared over 2,
minus 2x squared, right? Okay, minus,
9x to the third over 3,
which is minus 3x cubed, right? Okay,
plus x to the fifth.
okay, and that's from minus 2 to 1. Okay, so the 1/2 out front. This one better turn out positive. Anyone want to make a guess why? Everything's positive in y, so better come out positive. Second? It certainly would. Okay, 12 times 1 is 12, minus 2, minus 3, plus 1/5. I love doing the ones, almost as well as I like doing zeros. Okay. Now, the minus 2 is going to be the tougher part. It's minus 12 times a minus 2, which is going to be plus 24, right? I hope. Okay, minus a minus, which is plus. 2 times 4 is 8. And then minus a minus, which would be plus, times another minus, would be 24. Okay. I did the ones here. You just do a 12 minus 2 minus 3 plus 1/5. Okay. All right with that. Now, when you do the minus 2 here, because you're doing the minus, it's minus 12 times a minus 2, which is minus times a minus is plus 24. And then the minus times a minus would be a plus. When you put a minus 2 in there, it stays plus, so that becomes a plus. 2 times 4 is 8. Then you do a minus, which is plus, but when you put a minus 2 in here, that'll be a minus 8. 3 times minus 8 is minus 24. The first minus is because it's the lower number, that makes it a minus. Okay? But then this was already a minus, so it's minus a minus, which makes it a plus. And then you put a minus 2 in there, and it makes it a minus 8 times 3. Yeah, got it? No.
You put the -2 with the 12. What am I getting negative?
Okay. Yeah. Put the minus 2 in there, it becomes a minus 8 times, okay. Because you're doing the lower number, you're negating all those signs. So that would negate, and that becomes a plus. Okay, and then you 3 times the negative negative 2 cubed, which is going to be negative. So it's a minus 24, I think. You don't see that.
It's a -2.
Right.
It's in here. How is that?
Okay, well, wait. Let's do something up here. You're integrating from A to B of x minus x squared minus x cubed plus x to the 5th. Okay? Dx. I'm leaving out the coefficients. Keep it as simple as possible. Right? So this would be x squared minus x cubed over 3 minus x4 over 4. No, I messed up something. I put... No, there. I should have done... Wait. Let me go back and make it simpler. I mean, I was trying to make it simple and I went to the wrong place. Okay, let's start over. All right. I was trying to take out coefficients, but I was looking at the wrong thing. Let's just do 1 minus x squared plus x to the 4th. That's what we're integrating, dx. Okay. Then this would be x minus x squared over 2 minus x cubed over 3 plus x5 over 5. Evaluate it from A to B, right? Okay. Now, if you plug in the b first, that would be b minus b squared over 2 minus b cubed over 3 plus b fifth over 5, right? Now, when you go to the lower number, you negate all those things. That would be a minus a plus b a squared over 2 plus a cubed over 3 minus a fifth over 5. Right? Okay. So that's why you change the signs when you're doing this one. So that becomes a minus 12 times a minus 2, which is a plus 24. A plus 2 times a plus 4, because that doesn't change the sign, that's a plus 8. Then a plus 3 times a negative 8, which is minus 24. And then a minus, but then that would be a negative 32. So that's going to come up being a plus again, right? So the last one would be a plus, and isn't that 32 over 5? I hope so. All right, now let's see. The minus 24 and plus 24, they go away. And you got 12 and 8 are 20. Minus 5 is 15. So it's 1/2 of 15. And this adds to 33 fifths. All right. Ooh. Ooh. So let's see. 5 times 15, is that 75? Are we out of time?
Yes.
Oh, yuck. I'm hoping it's 75. 75 plus 33 is 108, and half of that is 54. 54 fifths. And let's see if that's right. 54 fifths divided by 9 halves. That'd be 6. You don't tell me. Yep, that would be 12 fifths. Wow. Okay, I didn't think in a hurry I'd ever get it right. So 12 fifths would be 2 and 2 fifths. So that would be somewhere right about there. Oops, there. So it would be right about there would be your centroid. And that looks maybe about right. Doesn't quite look good, but something like it. All right. We've still got example 6 to go. Yeah. But we're almost through with this section, I think. Yes. I mean, just one little example. So homework exercises, do either 5 or 7. They're both at calcchat.com. 7's at calcview.com. Do number 9, it's at calcchat. Do number 11 or 13. They're both at calcchat. 11's at calcview. Do any of the odds 15 to 27. They're all at calcchat. 15's at calcview. Do 29, it's at calcchat. 31 or 33, they're both at calcchat. 33's at calcview. Do 35, it's at calcchat. Either 37 or 39, they're both at calcchat. 37 is at calcview. If you want to, you can try to do 41 or 43. They should be at calcchat. If they're not there, don't even mess with them, unless you want to. That's up to you. Any of the odds 45 to 49. Oh, wait. Yeah, they're all at calcchat. Okay. And then 51 or 53 or 50, or 53, those should be at calcchat as well. Okay, we'll do the rest of them next time. Good. All right. Sorry we ran over, and sorry the math got so awkward. Calculus is the easy part. It's the arithmetic is the hard part. Sometimes. All right. Take care. I'll come get my key in just a few minutes.